All right, today we are getting our hands dirty with some serious robotics. We're going to walk through a full stack implementation of advanced force control, all the way from building a perfect digital twin to getting a UR5e arm to perform tasks that require a gentle touch. Let's get right into it. So here's the big question, right? How do you get a robot to do more than just move to a point in space? How do you teach it to interact with the world? We want it to trace a line on a surface, but not just trace it. We want it to do it with a perfect, constant amount of pressure. This is the core challenge of force control, and it's what separates a simple pick-and-place machine from a robot that can truly manipulate its environment. Look, before we can even think about writing a single line of control code, we have to start at the foundation, and that foundation is a perfect model. We need to build what's called a digital twin, an analytical model that is an exact mirror of our simulation. If there's any mismatch, any error here, every controller we build on top of it will be fundamentally flawed. Okay, so here's our stack, the tools for the job. We're running our simulation in MuJoCo. The robot itself is a UR5e with a Robotiq gripper, and we're using the fantastic menagerie models. For the math, the brains behind the model, we're using Pinocchio. The number one goal, our first mission, is to make absolutely sure that what Pinocchio calculates is exactly what MuJoCo simulates. And this is where reality hits, right? It's so easy to make naive assumptions. You might think, oh, I can just command torques directly, or the gripper doesn't weigh much. But the real menagerie assets are way more detailed. They have actuator models with gain and bias, and that gripper, it has significant mass and inertia that you absolutely cannot ignore. Getting these details right is the whole ballgame. And let me tell you, this was a huge lesson. For a while, the models just weren't matching up, and the culprit was right there at the end of the arm. The gripper's inertial properties hadn't been fully accounted for in the Pinocchio model. It's such a critical takeaway. Your payload, your end-effector, it's not just some optional detail. It fundamentally changes the physics of the robot. And boom, here are the results of getting it right. We cross-validated two key things. First, the gravity vector, G of Q. That's the force of gravity trying to pull on every joint. Then the mass matrix, M of Q, which is basically the robot's inertia. And look at those errors, on the order of 10 to the minus 5 and 10 to the minus 6. That is incredibly close. This is how we know we have a true digital twin. Yeah, this number right here is our green light. A maximum error of just 3.34 times 10 to the negative 5 on the mass matrix, that's insanely good. This isn't just for show. This precision means that when we design a controller based on our model, it's going to work exactly as we expect in the simulation. No nasty surprises. All right, our model is locked in, it's validated, now let's put it to work. The very first, most basic thing we can do with this powerful model is to simply defy gravity. The idea here is actually pretty simple, but it's incredibly powerful. At every single moment, we use our Pinocchio model to calculate exactly what torques gravity is applying to each joint. Then, we command our motors to apply the exact opposite torques. They cancel each other out perfectly, and the robot just floats, holding its position as if it were weightless. And the proof is right here. While holding a pose, just floating there against gravity, the maximum error on any joint was less than 9 micro-radians. I mean, that is an unbelievably stable hold. It's rock solid. And it tells us our model is spot on and our gravity compensation is working perfectly. Okay, so we've made the robot weightless. That's cool for holding still, but we want to move. So let's layer on our next controller, impedance control. This is where we get to define how the robot feels. We can literally program it to behave like it's attached to a virtual spring and damper. It really breaks down into 3 key steps. First, you figure out where you are versus where you want to be. That's your Cartesian error. Second, you use that error to calculate a force, just like a spring would. The further away you are, the harder it pulls. And finally, the magic step, you use the Jacobian matrix to translate that pushing or pulling force into the exact joint torques needed to make it happen. Now, here's a pro tip, something you learn in the trenches. That first step, calculating the error, can be tricky, especially for orientation. If you use something simple like Euler angles, you can run into all sorts of problems, like gimbal lock. The robust way, the right way, is to use a lie log map. It gives you a clean, stable way to represent that orientation error, so your controller just works no matter how the robot is twisted. All right, this is where it all comes together. Our digital twin is solid. We can cancel out gravity. We can move through space with a programmable feel. Now it's time for the main event, actually making contact with the world in a controlled, intentional way. The strategy we use for this is called hybrid position force control. It sounds complicated, but the idea is actually super clever. You just split the problem in two. For the directions where the robot can move freely, in our case, sliding along the table in an XY plane, you use a position controller. But for the direction where it's constrained, pushing down into the table on the Z-axis, you switch to a force controller. Simple as that. To control force, you absolutely need a clean force signal. And this was a bit of a gotcha moment during development. The first attempt used a sensor that picked up all sorts of other forces in the system, creating a noisy, unusable signal. The fix? Switching to a specific MuJoCo function that only reports the pure contact force. Getting that clean signal was the key to making the whole thing stable. And look at this. The results are just wow. We targeted a 5 Newton downward force with a tolerance of plus or minus 1 Newton. Using just a simple PI controller on our clean force signal, we stayed within that target band 99.96% of the time. That is incredibly stable force regulation. The robot is holding that pressure just perfectly. All right, time for the final exam. This is the capstone project. We're going to take every single piece we've built so far, the gravity compensation, the impedance control, the hybrid force control, and combine them into one single, pretty challenging task. So here's the mission. The robot needs to come down, make gentle contact with the table, press down with a constant 5 newtons of force, and while holding that force perfectly steady, it has to trace a clean 50-millimeter line. It's the ultimate test. Can you manage both position and force at the same time, accurately? So, how do we do? Let's look at the numbers. We stayed within our force band over 94% of the time, which is really solid, especially while moving. And our maximum position error while tracing the line was only 1.7 millimeters. That's a great result that proves the whole stack works together. Sure, we could probably tune the gains to get that position error even lower, but this is a fantastic proof of concept. So when you step back and look at what we've built, it's pretty amazing. We went from a purely theoretical model to a dynamic simulation where a robot can perform a delicate task that requires a sense of touch. By carefully building up these layers of control, we've created a system that can truly feel and interact with its environment. And that really makes you think, doesn't it? Once you give a robot a sense of touch, what becomes possible? Think about manufacturing tasks like sanding or polishing or delicate assembly. Think about sending a robot to a remote location to perform a repair. This kind of technology is a real game changer. So I'll leave you with this. Now that we can do this, what's the next big challenge we should solve?